there are several methods that use jet substructure to find signals of interest in the LHC data. That is, you look not just at one big jet, but at what's inside of it, and try to figure out if that's a jet that came from something you're really looking for, an exciting new particle, or something that's ordinary QCD kind of process. And it's fun to talk about that because we're in a very exciting era where the LHC is now running, well, it's not running just this instant, but it has been running for 2 years. We've heard a lot of results in this workshop from LHC, and they're shut down for a year or so now, but then they're going to start running again with higher energy. So there's lots of opportunities to find new things, or else maybe rule out that there's any new things. But either way, it's going to be an exciting time. So to find new things, one avenue is this field called jet substructure, which has had a lot of work on it, both experimental and theoretical, over the last, I would say, 5 years. And this talk is about the structure in nature that the various methods that people develop try to take advantage of. So I'm not going to try to tell you about particular methods for using jet substructure, but rather about what's in nature that it is that you're looking for. That way, if you hear a talk about jet substructure and you say, person did this, that, and whatever, made these cuts, you'll have some idea of what the reason was behind the way it was organized. So we're looking for a signal, but there's background events. So at the LHC, we're looking for the signals, but there's many more background events usually. So where I live in Eugene, Oregon, in the United States, there's quite some number of background creatures like that one. Lots of background creatures. And there's a very, very few signal creatures that might be more interesting. So I've got a picture of a signal creature. There it is. And we like to now tell the signal creatures from the background creatures. So you write a computer program to tell those apart, and unfortunately, you won't tell them apart unless you're fairly clever, because, well, the background creature has a bill, the signal creature has a bill. The background creature has wings, the signal creature has wings, and the background creature has webbed feet, and so does the signal creature. So if that was your computer program, then you just identify both of those as the same. And what you have to do is look for the things that are different. Now in this case, there's one crucial difference, is the signal creature can't swim. So we just toss them into the lake and you'll see. In the real case, it's a little more complicated than that because there's mutations on the background creatures. So sometimes the background events creatures look just like the signal creatures, but that's rare when that happens. So what you're going to come up with is a statistical method to say there's a high probability that this is a signal. That you can't say for sure on any one of these creatures. Okay, so let's now talk about signals and backgrounds at the LHC. I take a signal event that you might be looking for to be something in which one or more new heavy particles, or maybe old heavy particles, is created and then decays. And sometimes in the signal events, there's a chain of decays. In the one I'm looking at just in this diagram, there's just one. And top quarks in particular, and I'll talk about top quarks later, top quarks could be part of the signal of something really new, or it could be part of background. So here's an example. This is a production of a Higgs boson decaying, recoiling against a Z boson. And the Z you can just tell immediately because it decays to be plus or minus. So that's easy to see. But supposing the Higgs boson decays to be V bar, then could you pick that out against the QCD background? So and then try to sort that out and see if the pattern that's in these subjects looks more like the signal kind of jet or the background kind of jet. And this is especially useful and was developed first for this kind of action, for this very process was the first example of this kind of method. It's helpful that if this jet is highly boosted, meaning it's got a lot of transverse momentum. Okay, so what does quantum chromodynamics have to say about sorting out the signal from the background? You can use field theory to understand the characteristics of the background events, and use field theory to discover the characteristics of the signal events, like in the particle case. So then the schemes for discriminating between the two depend on using the similarities and the differences between those. And that's what I want to talk about. So first, similarity is initial state radiation. Both the signals and the backgrounds have initial state radiation. So here is our signal event. Well, I dressed it up, so now my B quarks radiated some gluons, so it's getting to look a little more complicated. But furthermore, incoming quark, incoming anti-quark, both radiated gluon in this particular event that I drew. And the gluons can, one or both of them, can come in the same angular region as all this stuff from the Higgs decay. Similarly, here's a background event. There's still a Z boson, so it's going to look pretty similar, but now there's no Higgs boson. There's just a gluon. The gluon splits to 3 gluons. And that's got some initial state radiation also. So having all that initial state radiation makes the separation of signal and background more difficult than it would have otherwise been. So what's going to distinguish the signals from the background? Mass bumps. That's the first obvious thing. If you look at the Higgs decay, goes to BB bar, the total momentum squared of the B and the B bar add up to the Higgs mass squared. So if you can figure out what to look at there, you just add up that momentum, square it, and you see it should be the Higgs mass. And really with very small uncertainty, because the uncertainty on this, if you have infinitely good measurements, is the mass of the Higgs times the width of the Higgs, and the width of the Higgs is small. Actually, the practical uncertainties are way bigger than that. Okay, so we learned that we should be talking about masses. Let's talk about that. How about masses in background, in QCD events? So here I drew a gluon splits to 2 gluons. And how about the mass of the 2 gluons? It's going to be convenient to take the virtuality of the 2 gluons, B1 plus B2 squared. And for purposes of talking about the QCD of this, divided by the P1 plus P2 dot Q naught, where Q naught's the vector that's at rest in the center of mass frame of the whole event. Just for technical reasons, it's convenient to divide that out. But if we look at events in which P1 plus P2 is relatively fixed, then we're looking still for a bump in V in the signal event. And how about in the background? What's the distribution in this thing V in QCD events? So here it is. You look at Feynman diagrams, square the right Feynman diagrams, and integrate over the momentum fraction in that splitting. So how much fraction of the longitudinal momentum of the mother parton is carried by one of the other 2 daughter partons. Integrate over that for the moment. That's integral dz. And then what you get? The number of particles is dv divided by v. Times a constant, times alpha strong, and times a logarithm of v, which came from that other integral. So that background, that's a smooth background. There's the shape of it. Just 1 over v. And on a signal, assuming that P1 plus P2 is held constant, then the signal talk some more about the QCD events. What if we have two gluon splittings like this? Then there's a convenient approximation, which is going to be pretty useful. Let's suppose V2 is less than V1. Well, it usually will be if there's a big cross-section for doing this. And if V2 is small compared to V1, in calculating the splitting for V1, let's set V2 equal to 0. Then what does the differential number of events look like? dn is dv1 over v1 times alpha strong in a log, and times dv2 over v2. It's just the product of two independent distributions. And put in there a theta function that says v2 is less than v1. So that's just generically characteristic of the QCD events, that not only is there dv over v distributions, but those distributions are nested. Okay, so let's look a little further. Let's talk about an application of this. Here's our Higgs boson, and those dv over v distributions are peaked at small v's. So the Higgs boson, the mass of everything there is likely, it should be, if it's a signal event, it should be the Higgs mass. That's 126 GeV. But if I look at the subjects, that's subject 2, that's subject 1, they have small masses. Because it's dv over v, the v's tend to be small. So what you should look for is take your two subjects and find two subjects have a small mass, but if I put it all together and calculate the mass of everything together, that's a big mass. So going from everything together to the subjects, there's a mass drop. And you can have your computer program look for the mass drop. And in the first paper by Butterworth, Davison, Rubin, and Salam about this general class of subjet analysis, finding the mass drop was a big part of the way they did it. Okay, but I should tell you about a little more. There are pseudo factors. So it wasn't quite true what I told you, dv over v, because we haven't taken into account virtual graphs or emissions that were too close to being a very small v that we couldn't resolve them. If we do take all those things into account, then we find we need a pseudo factor. That's this factor here. And in my previous lecture, I talked about it in a sort of hand-waving way, but here I've really written it down. What is it? Exponential of minus the integral dv over v c alpha s log of v tilde over v. It's the same as the splitting function. It's the exponential of minus the integral of the splitting function with limits from v1, so v1 was the virtuality of the mother part-time here, down to the v you're observing, that's this v. And you can interpret that as the probability that this part-time had a chance to split with any v, and it didn't split until it got to the v that's listed here, this v. So the probability that it didn't split is this exponential minus the splitting probability. And that accounts for virtual graphs and unresolved real part-time emissions. So does that matter? Here's the same formula that I wrote before, this one right up here, and I just made a plot for a particular example. Here's v on the horizontal axis, here's dn dv on the vertical axis, and if I don't put in the pseudo factor, I get something that grows and grows and grows and goes right up to infinity. But that's not what really happens. It's not likely to have a v that's super small. In fact, with the pseudo factor cuts it off for very small v's. Why? Because if I set v going to 0, this gets to be exponential of minus infinity. And that's more powerful than 1 over v. So the pseudo factors are important, and it's actually easy to take those into account.
So why
v tilde, I said there's another integral inside of this. So there's an integral dz. And we'll get to that in just a moment. But this logarithm comes from doing the other integral. And it's going to be the log of v, or the v bar inside of this integral. But it's normalized by something depending on the starting conditions of the splitting. So I think we'll see that in.
So v tilde is comparable to here, v bar.
V tilde is sort of comparable to v1, but it's something you calculate. It's when you do the splitting. I just abbreviated it as v tilde. So really, what this should be is dv bar, dz of the splitting function. And I performed the z integral. And performing the z integral got me that logarithm. But I didn't show you. I didn't show you that because I haven't talked about the z integral yet. I'm allowed to talk about the z integral. And there's one more variable besides the virtuality v, and it can either be the momentum fraction z, or it can be the angle between two partons. So here I'm going to talk about it in terms of the angle. So here's two daughter partons, and there's an angle theta 1, 2 between them. And theta 1, 2 is not determined by just v. You get to integrate over theta 1, 2. Kinematically, it can't be too small because, well, evidently, if theta 1, 2 goes to 0, then v has to be 0. If two partons are just exactly collinear, then the virtuality is 0. So there's a limit. Theta 1, 2 has got to be bigger than v divided by something having to do with the external kinematics. So if, as soon as you get to theta 1, 2 larger than that, but not extremely large, then you can ask what's the n, what's the distribution in angles, and it's d theta squared over theta squared. In fact, d theta squared over theta squared is what gave me a logarithm. How about very large angles? Large theta 1, 2, oops. Large theta 1, 2 corresponds to P1 much less than P2, or the other way around. So the absolute value of P1, that's the transverse amount of P1 transverse to the beam. Or it could be, if this is like a positron annihilation, it could just be the absolute value of P1. Either way, if P1 gets to be very, very small, that corresponds to large theta 1, 2. And that means that the gluon is what we call soft. So in the case that we emit a soft gluon, interference with emission from one parton, say we're emitting a soft gluon from parton 2 here, we have to account for interference between that emission and emission from somewhere else. And in the leading color approximation that I explained in the second lecture, there's a color-connected partner, which in this case, the color-connected partner of P2 is PK, what do we label here? PK, and here it is. So you just imagine that each of these gluons has a little line. You just draw a line backwards from here and up to there, and you see what's the color-connected partner. So what we're really doing for large angles is we're emitting from a color dipole consisting of parton 2 and parton K. And that modifies the color dipole nature of this, modifies the angular distribution. So it's not really the theta 1, 2 over theta 1, 2 squared. That's times a factor. Now what you really, to be So here's what the factor is. It's stated angle between 2 and k, that's that angle, that's the big angle, divided by angle between 1 and 2 plus the angle between 1 and k. So I just made a graph on the next slide to show you what that angle factor looks like. Here's a 3D plot of just that function, this function right here. Here's where parton 2 is, there's where parton k is, and what this extra angular factor is doing is modifying the d theta squared over theta squared distribution so that we see it's more likely to have an emission between parton 2 and its color-connected partner, parton k. The reason for that is that there's constructive interference between emission from number 2 and number k. And G here at the peak is equal to 2, and right there is equal to 1. So there's a factor of 2 worth of positive interference. And actually, if I go the other way, out here, there's negative interference. Also, out here, there's negative interference. So it's not likely to get angles of emission that are a lot bigger than the angle between 2 and its color-connected partner. And it is likely to have emissions between them. Okay? And you see that by this amazingly simple formula. So let's think about application of that. Here's a Higgs boson that decays to a BB bar. And then the B and the B bar are emitting some gluons. So let's ask, in what angular region are those gluons likely to go? So here we emitted a gluon from the core. The color-connected partner of the core is the antiquark. And the color-connected partner of the antiquark is the quark. So it's more likely to have these gluons emitted in the angular region between the B and the B bar. More likely that than to emit them on the outside region. On the other hand, let's look at a background event. We're trying to figure out what's different between background events and signal events. So here's a background event. That's a gluon goes to BB bar. But now here's a B quark, and the color-connected partner of that B quark is the color-connected partner from this gluon, which is off here somewhere. It's not the anti-B. In fact, the color-connected partner of the anti-B is some other thing that's outside of this diagram. So it is more likely to emit these soft gluons in the angular region outside of the region between the B and the B bar. So just that difference of angular distribution is helpful for distinguishing the signal events from the background events. And there's a variable that codifies that. It's called pull. Okay, so next thing I should tell you is that gluons like to be soft. In fact, there's just a translation between the angle between the two gluons that are emitted and the fraction that one or the other of them carries, which we're calling fraction of the momentum, z. And here I just wrote the relationship. Z times 1 minus z is v over theta squared times a kinematical factor. So large theta means small z, or else small 1 minus z. And small z means large theta. You can just write things in terms of either z or theta. So the fact that there's a d theta squared over theta squared distribution means that large thetas are important up till you get to this sort of cutoff from where the angle of the color-connected partner is. So large theta is important means small z's are important. So we expect to have lots of small momentum fraction gluons emitted, lots of soft gluons, and they're emitted then at wide angles, up to some kind of limit.
Z is small, and when Z is close to 1, also has the same.
Yes, so Z is small means one of the gluon number 1 was soft. 1 minus Z is small means gluon number 2 was soft.
Oh.
Either one could be soft. they typically, they have quite low transverse momentum. Sometimes non-perturbatively low. So we have to try to sort that out. Okay, so we've covered angular distributions, soft gluons, dV over V distribution. I think we're ready to deal with a somewhat different topic now. What if I have a heavy particle with color? Then what happens? So I'm going to switch now examples from bottom, from Higgs boson to a top quark. So let's imagine we're going to try to find top quark jets. Top quarks are like Higgs bosons in that they decay, but they're not like Higgs bosons because they're covalent. So a top quark coming out here can emit a gluon. Then what happens? How do you describe that?